Good morning. Today we start a 3-lecture unit on statistical process control, and I'll be honest, this lecture has the most amount of mathematics and the least amount of semiconductor content of the three. Statistical process control is the oldest idea in this course. Walter Shewhart at Bell Labs 23 years before the transistor, and yet every modern method we study later, including the machine learning ones, answers Shewhart's questions. When we get to fault detection on equipment, sensor traces, to autoencoders flagging anomalous edge runs, the logic has not changed. Only the dimensionality and the functional class have. We spent today on statistics to make you statisticians. 4 or 5 ideas: variation, standard deviation, the z-score, the sampling distribution, and the 2 kinds of error recur all semester. Solid, and everything downstream is straightforward. I assume no statistics background. If you have had probability, parts of today are revision. Be patient with your classmates. Here is what you should be able to do working out. First, explain why variation, not the average, destroy yield in a fab. Most arrive thinking quality means hitting a target. It means controlling the spread. Second, distinguish the common cause for special cause variation. Name the right response to each opposite actions, and confusing them is expensive both ways. Third, compute and interpret the mean, standard deviation, and the z-score. Computation is easy, interpretation is what I will test. Fourth, explain why an average 5 measurement scatters less than a single one. The entire reason control charts are built as they are. Fifth, the one connecting today to the rest of the course. Frame is the process out of control as a decision with 2 kinds of error, each costing differently. Take away the fifth. A control chart is a hypothesis test run over and over, and its design is an economic trade-off, not a statistical truth. Let's look at an example. A logic fab is running a gate etch. In week 1, a chamber drifts, no alarm, no error. A seal degrades, the etch rate creeps, and the critical dimension wanders upward around lot 65. Here is an important part. Those wafers are all still inside the specification window. Metrology measures and passes them, no red light anywhere. In week 3 at electrical test, the first point where you learn whether the transistor works, a parametric failure shows up. Threshold voltages are out. Somebody investigates and traces it to that chamber. 40 lots, depending on the product, $2 to $8 million of material plus 3 weeks of team's time plus the schedule slip. My question, and I want a real answer. The data existed on day 1, every number measured and stored. What would somebody have plotted and compared it against to see this in week 1? Here is the arithmetic that governs the fab. Suppose a single process step is 99.9% good. Sounds excellent. You would congratulate the engineer. Now run 1,000 of those in series. What is the final yield? 0.999 to the power of 1,000. 37%. 63% of your wafers are gone. Yields multiply. Each step is a filter. Survivor of step 1 are the input to step 2. Small per step losses do not add, they compound. Here, look at the curves. The 1,000-step curve is almost flat and then rises like a wall at the end. That geometry is why semiconductor manufacturing feels as it does. Everything is fine, and then a tiny degradation in one step drops you off a cliff. The corollary? There is no unimportant step. A step that looks already excellent is where the remaining yield hides. So let's be concrete about the cost. Poor control is expensive is a slogan, not an argument. The direct costs first. Scrap material, a 300mm wafer at a late metal layer carries months of processing value. Every one of those 1,000 steps added cost. The 25 wafer lot scrapped after metal 1 is a 6-figure write-off, more in the high value product. Tool downtime. The tool comes down for a diagnosis, cleaning parts. Capacity you paid $20 billion for and did not use. Requalification. After a fix, you run the monitor wafer, show the tool is back inside its window. Hours at best, days if the fix was invasive. All of these three show up in a monthly report. Somebody counts them, somebody is accountable, so they get attention. There are also the smaller half of the bill. Next slide has the ones nobody counts. So one sentence, and we spend the semester unpacking it. Detect a real change quickly without reacting to noise. Both halves matter and they pull against each other. Quickly, damage scales with how long you take. 40 lots in that first example. Real. A perfectly normal process still produces measurements that wander. React to every wiggle and you make things worse. I'll prove that with a simulation in 15 minutes. A promise about this course: every method we study is a different answer to that one sentence. We ran rules in lecture 2, the EWMA controller in lecture 3, Hoteling's T-squared in multivariate modeling, reconstruction error from an autoencoder on equipment sensor traces, which some of you will implement in your projects. They differ in how much data they use and how many assumptions they make, not in that they are what they're for. So when a method seems arbitrary later, ask which half is improving and what is giving up on the other. All right, so I wanted to run an experiment. This container holds 1,000 beads, 800 white and 200 red. Thoroughly mixed. Red beads are defects. Now, let's say there is a production worker. That person's job is to produce the white beads. They dip this paddle in and draw 50 beads. Whatever comes out is the output for the day. The rules are simple and I want them to be followed exactly. Do not tilt the paddle, do not sort and pick out the beads, work at the same pace as everyone else. This is a standardized process and we expect standardized work. The management's position is straightforward. Good workers draw fewer red beads, poor workers draw more. We post results publicly and recognize the top performance and coach the ones that are struggling. This is how quality improves. Now, before we start, let's commit to the prediction about who will do the best. All right, so let's look at an example, round 1 result. The best work was done by a group that drew 7 red beads against a group of average of nearly 11. We tell them, keep doing whatever you are doing and show the others your technique. Now, this is not acceptable for the other group that produce 15 red beads. We say to them, this is not acceptable. 15 red beads, more than the double of the best performer, same procedure, same equipment. All right, so now let's look at this in this way. Same container, same paddle, same procedure, same 50 draws. One gets 7, one gets 15. What is the difference between them? To understand this, let's run 2 more rounds. Now let's look at round 2 and 3. Now our employee of the month, whose technique everybody was to copy, go noticeably worse. The one on the performance plan improved substantially. Nobody changed anything, no coaching, no change of the container or the paddle. So basically we are watching the regression to the mean. Extreme result is extreme partly from the process and partly from luck, and luck does not persist. The next observation will on average be closer to the middle. So let us name what happened. Every worker drew from the same container, same procedure, same rate, one process, and all the variations was operating normally. The common cause variation built into the system always present, producing a stable and predictable band. Predictable is the key word. I could have told you beforehand roughly what the range you would get. In a fab, chamber to chamber differences, gas purity, ambient temperature, metrology, noise, incoming wafer variation, dozens of small contributors, none dominate. You cannot fix it by acting on one result. Reducing it means changing the system. The special cause is the opposite. Sometimes specific thing happens, a wrong recipe is loaded, a gas leak, an RF match failure, new resist batch, it breaks the pattern and you will you go find that thing. The chart will not say what it was, but it says roughly when, and in the fab, a timestamp is enormously variable. So all of these things points to the final thesis. Different causes demand opposite responses, and you cannot tell which you face from a single measurement. You need a pattern over time. This is common cause in time order. 60 consecutive lots of H rate. Is any point surprising given the others? No, everyone is unremarkably next to its neighbors and the scatter is consistent throughout. The band is stable. Stable means predictable. I can tell you what tomorrow's lot looks like, and that is operational definition of control, not good but forecastable. The correct response is to leave it alone. If someone says lot 42 was low, bump the power 2%, no, that is noise, and adjusting for noise makes things worse. But there is an important caveat. If the band is too wide for the specification, that is a real problem. But a system problem, not a lot problem. You change the tool, the recipe, the measurement, not the lots. The distinction from lecture 2, a stable process is not necessarily a good one, only a predictable one. Stability and capacity are separate questions, and confusing them is a very common error. Now let's look at the special cause, two flavors on one chart. First, the while point at lot 19, far outside the neighbors, then back to normal. A discrete event, somebody loaded a wrong recipe, which happens on a high mix line where the operator runs 6 products. Second, and more dangerous, the sustained shift from lot 36. The level drops and stays, not one bad lot, but every lot from here at a different operating point. Gas flow drifted, a mass flow controller degrading. The while point is dramatic and gets attention, and the shift is quiet and does far more damage. Go find that thing. Chart earns its keep here. It does not name the cause. It tells you where to look and when. It started at lot 36 is enormously actionable. You put that date's maintenance log, shift change, material lot, prevented maintenance, recipe edit, and the search narrows from 3 months to that Tuesday. That is how root cause get found in the fab. The chart's timestamp gets you query everything else. So I promised to prove that overreacting makes things worse. Here it is. Both panels are the same process, pure common cause noise, sigma of 1 centered on target. Left, we do nothing. Sigma comes out at 1.01 as expected. Right, we are aware. After every lot, we measure the deviation from the target and apply an equal and opposite correction, and this is what a diligent engineer does. Sigma 1.48, 50% worse, and with more aggression, it diverges entirely. So each correction responds to noise, not a shift. It moves the process of target by exactly that random amount, and the next lot's noise lands on the offset you just introduced. So the errors accumulate instead of cancelling. So now hold this for lecture 3. It is precisely the failure mode of an over-tuned run-to-run controller, and EWMA weight is literally a knob that sets how much you tamper. Set it to 1 and you get the right-hand panel. So here is the highest value plot in the process engineering, and it needs no statistics. H rate 120 consecutive logs in the order produced. A run chart, and that is the whole technique, plot the data in time order. So what do we see? A real process engineering with no mathematics, a repeating structure, resets, and perhaps the inference that something periodic is happening to the chamber. So what is really happening? A seasoning cycle with preventive maintenance resets. We'll come back to it. So before any statistic, any control limit, any model, plot the data in time order and look at it. And I have seen sophisticated analysis done on the data a run chart would have explained in 10 seconds. So that's the value of the run chart. Now what most people do with measurements, a histogram. Same 120 numbers, nothing discarded, every value counted into a bin. Useful plot, centered around 992, the spread, a roughly symmetric shape with no obvious outliers. But something has been thrown away, and it is not obvious the order they arrived in. Which came first? You cannot tell. The histogram has no memory. The sawtooth, we spent 2 minutes identifying ramp reset periodicity is invisible, shredded into these bars. So the histogram is a summary, a run chart is a story. I labeled this because students who learn histogram first spend the course believing SPC is descriptive statistics. This is about how a distribution behaves over time. Throw away time and you throw away the signal. So let me prove that with the more convincing example that I know. Two processes, the run charts on the left. Process A is stable, noisy but stable. Constant level, constant spread, no tread. Process B falls off a cliff, declining monotonically across the whole run. If this were your H rate, you would have had a bad week. Now the histograms on the right. They are identical, not similar, identical. Process B is the same 120 numbers. Process A sorted. So every summary statistic matches the same mean, standard deviation, skewness, kurtosis, minimum, maximum, median, interquartile range. Any capability index, lecture 2, comes out identical. One of these processes is failing. The only thing distinguishing them is the order and the order in the entire signal. So when someone hands you a mean and a standard deviation, ask if the process is okay. Your first question is always, can I see it in time order? Give them the reading habit here, level, spread, pattern, in that order every time. A change in the spread is often the earliest warning, the one that people will miss. So SPC is about distribution over time. No distributions. A distribution along can hide a catastrophe. Not the time series in general. We are not forecasting next Tuesday's value. What we care about is how a distribution behaves as time passes. Is the center where it was, the spread, the shape, and when not, what did change? Everything else today, standard deviation, normal curve, z-score, the central limit theory, is machinery in service of that sentence. In lecture 3's multivariate methods and the machine learning later, the sentence doesn't change, only the dimensionality does. A 100 sensor on an edge tool at 10 Hz is still a distribution over time and just very high dimensional, and you need principal component analysis or an autoencoder because you cannot eyeball a 100 dimension. But the question is identical to the one we asked about this 1H rate signal. 4 patterns you will actually encounter, each pointing to different class of physical cause. Drift, a steady trend one way, almost always a consumable wearing out. CMP pad wear, a sputter target eroding, chamber walls accumulating coating, filament aging, anything monotonic with usage. Step, a level jump and stays. Something discrete change, a recipe edited, a chamber swapped, a new material lot, an operator changing a setting. Instantaneous, a strong clue before the physical degradation rarely is. Sawtooth, gradual shift with a periodic reset, seasoning, plus preventing maintenance, extremely common, frequently misdiagnosed as instability. The process behaves as designed, a design included in a drift reset cycle. Charting it natively consume constant alarm. Cycling, a periodic oscillation, shift-to-shift differences, day and night ambient swings, or importantly, an auto-correlated controller overcorrecting. That last is the final experiment in production. In lecture 2, each maps onto a run rule. The Western Electric rules are pattern detectors tuned for these 4 shapes. Now we build the standard deviation. No formula, we derived in 5 moves because the formula is opaque and construction obvious. 5 wafers from lot 998, 100, 1006, 1001, 993 and 102 angstrom per minute. First the mean. Sum is 5000 over 5, exactly 1000. Next, the obvious question, how far is each point from center? 998 is 2 below, 1006 is 6 above, 1001 is 1 above, 993 is 7 below, 1002 is 1 above. Minus 2 plus 6 plus 1 minus 7 plus 2. Step 1, and everybody can do it, 5 deviation about the mean. So the average these 5 and call it the typical distance from the center. Square is deviation, minus 2 becomes 4, plus 6, 36, plus 1, 1, minus 7, 49, plus 2, 4. All positive, problem solved, but the squares rather than the absolute values. Absolute deviation is legitimate. The mean absolute deviation is the real statistics. 2 reasons squares win. The squares are differentiable everywhere. Absolute value has a kink at the 0. That matters for optimization. least square regression exists because squared error is differentiable and most model you fit later minimize the squared quantity. Second, the one that matters today, squared quantities add across independent sources variation. Absolute deviations do not. That gives us this course more useful in 5 slides, and that is why variance decomposition, gauge, R and error budgets work. 7 becomes 49, dominating everything. Squaring makes measures sensitive to the outliers, a feature when outliers are what you hunt for. Step 2, which we now do on board rather than on a slide. The 5 deviations sum to exactly 0 because the mean is the balance point. That is why we cannot simply average them. And step 4, also on the board, averaging the squares gives the variance 23.5 here, but the units are angstrom square per minute square, which nobody can interpret. Hence the square root on the next slide. Take the square root. The square root of 23.5 is 4.85. Sigma equals 4.85 angstroms per minute. Now this is interpretable. Sigma is the typical distance from a measurement to the center and in the units you measured. The shaded band is a plus minus 1 sigma. Most point falls inside it. If a colleague says the CD sigma on layer 1 is 0.8 nanometer, you know the typical wafer differs from the average by 0.8 nanometers and a wafer 2 nanometers off this average is unusual. And that is the payoff of the 5-step construction. Sigma is not an abstract parameter, it is a distance. And we never needed the normal distribution. Sigma is the property of any numbers. The normal comes next, turning distance into probability. Note the divisor was n-1 equal 4, not 5. Computing the mean used up one piece of information, leaving 4 independent deviation. Name it, but do not derive it. So here is the formula. A description of what you did, not a notation. Deviation squared averaged over n-1 square rooted. 3 things. So what it is? A typical distance from the measurement to the mean in original units. Why n-1? You spent 1 degree of freedom on the mean, so 4 deviations remain. With large n, it hardly matters. And where it goes, the important card. Control limits are plus minus 3 sigma. Capability is a tolerance in sigma. Gauge R and R is the budget of sigma squared, all this number. So you'll not have to compute by hand anymore. We will use Excel, Python or Fab's SPC system, do it million times daily. The most useful equation in this course, and I have thought about which one deserves that title. The total variance equals within wafer plus wafer to wafer plus lot to lot. Variances and standard deviations do not. Fab variation come from distinct roughly independent sources. Within a wafer, center to edge differ a radial signature from the tool, between the wafers, chamber position effects, and between lots, material, and setup. They combine by adding variances, not the standard deviation. 60 plus 9 plus 4 plus 29, root 29 is 5.39 nanometers, not 4 plus 3 plus 2. And this is why we squared the deviations in step 3. With absolute deviations, the equation is simply false and nothing downstream works. Gauge R and R in this equation with measurement and process as 2 teams. CD and overlay error budgets are within a dozen terms. The students will add the standard deviation for this for the rest of their careers unless it sticks now. Let me show you it happening because the claim sounds like a magic and is not. Left, 1 random effect uniform between minus and plus 1. Perfectly flat, every value equally likely. Middle one, add 3 corners rounded, an obvious peak in the middle. Why? Many ways to total near 0 and only one to get near 3. All 3 draws near the maximum. Right, add 12. Indistinguishable from normal by eye, and it would pass most formal test. Notice where we started. Uniform, as unbell shaped as possible. We assume normality nowhere, it emerged from addition. Change the underlying distribution. For example, switch to exponential and bimodal and it still converges. That robustness is why the normal model is worth using when only approximately light. So let us learn to read that curve. So this is the picture to sketch from memory. Roughly 2/3 of measurement, 68%, fall within 1 sigma of the mean. 95% within 2 sigma, 99.7% within 3 sigma, 68, 95, 99.7. What memorizing? It lets you do the arithmetic in a meeting without a computer. And that last number means 3/10 of 1% outside, 0.27%. So with a perfectly normal process and a limit at plus minus 3 sigma, roughly 3 measurements in 1000 fall outside by chance. Nothing wrong, and that's the randomness. 0.27% is the origin of the 3 sigma control limit. Schubert judged 3 in 1000, rare enough to investigate and common enough not to be paralyzing. We will interrogate that judgment later. Now the most useful tool in this segment, the z-score. Z equals x minus mu over sigma. How many standard deviation is this measurement from the center? Our H rate, mean 1000, sigma 5. A lot comes in at 1011. Z equals 1011 minus 1000 over 5 equals plus 2.2. What does that mean? 2.2 standard deviations high, unusual but not alarming. About 1.5% of the lots land this high. We turned angstrom per minute into a universal unitless number and compared across different processes. The Z of 2.2 on H rate and 2.2 and overlay mean the same thing. And that is why I make a point of it. The z-score appears 3 more times today and in lecture 2 wearing 3 names. If you remember one thing from today, remember this. One idea, 3 names. Control limits. Upper and lower limits on the Schubert chart sits at z equals plus and minus 3. Beyond them is a signal, the z-score with a threshold. Capacity, CPK. Defined properly in lecture 2 is the distance from the process mean to the nearest spec limit in sigma divided by 3. The z-score over 3, CPK of 1 means 3 sigma over 3 sigma away, 1.33 means 4. Defect rate, parts per million out of specification, is the tail beyond that z times a million. 3 vocabularies, 3 chapters, 3 groups in a fab, process, quality, yield, all the same quantity, distance from the center in units of the process, own variability. And when capacity arrives in lecture 2, we'll come back there. CPK is the z-score with a different name and a division by 3. See that, and you never memorize that formula. So let us make that concrete. Gate CD, target 45 nanometers, sigma 0.8, upper specification limits 47.4, above that out of tolerance. Now let's work with them. Z equals 47.5 minus 45 over 0.8, and that is 2.4 over 0.8, exactly 3. So the spec limit sets at 3 sigma up. Tail area beyond z equals 3, 0.0135 times a million, 1350, 1350 ppm over the spec. Is 1350 ppm good or bad? It sounds tiny. 0.13%. Consider what it applies to. Billions of transistors on die and this one critical dimension on one layer. Even if few features are critical, 1350 ppm on a dimension, gating transistor performance is a yield problem, which is why fab targets well beyond 3 sigma on critical layers. A CPK of 1, this case is marginal. Automotive supply require 1.67, 5 sigma above, half a part per million. And you can compute that from a mean and a sigma. Now I have said the normal model works. Here is when it doesn't, both cases common in fab data. Left, particle adders, counts bounded below 0, no negative particles, skewed right. Most favor pick up a few, occasionally one picks up many, approximately Poisson. Modeling it as a normal process give nonsense, including negative counts. Right, the most important one, overlay from 2 chamber pooled. Each chamber is perfectly normal, around minus 3.5 nanometers, B around plus 3. Pooled, you get a bimodal thing, that is neither. The answer is almost never a fancier distribution. Unpool chart the chamber separately. A bimodality is not an inconvenience, it is actionable. Your chambers are not matched. Mixtures are commonest cause of an apparent non-normality in the fab data. Before reaching for a transformation, ask whether you pool two populations, chamber, shift, product, metrology. Usually you have. The same process, two ways of looking at it. Left, 200 individual wafer measurements from a stable process, sigma is 8.5 x by 8.4 angstrom per minute. Right, the same process, 5 wafers at a time, plotting each group's average, 200 subgroup averages. Look how much tighter is the right hand cloud. Sigma is 3.7 against 8.4. Be precise about what did not change. Same process, same tool, same recipe. Every measurement on the left is also inside one of the averages on the right. Nothing about the process change, only what you choose to plot. Rerun it so they see it, not a fluke. Ratio is stable. Beyond the formula 8.4 to 3.7, what is the ratio? Where does 5 come into? The ratio is square root of 5. 8.4 over root 5 is 3.68. The standard deviation on an average of n measurements is sigma over square root of 2. Averaging, let's see, high and low draw cancel. Root n rather than n causes variances add, and you divide a sum of n variances by n squared, and that equation working again. It drives a real engineering decision. N equals 1 to 4 halves the noise, a big win for 3 extra measurement. 4 to 9, a half to third, smaller win, 5 extra measurements. 36 to 25, 9 extra measurements by almost nothing. So in a fab, this is also a cost argument. Every extra site, CD same time, on a bottleneck tool, lots queued behind it, scarce resource, diminishing return. Which is why subgroups of 4 and 5 are near universal, not traditional, and where the curve flattens against metrology budget. The result underneath all of this has the name central limit theorem. In words, averages tend toward a normal distribution even when the individual measurements do not. That licenses everything that we build. The 3 sigma machinery, the 68, 95, 99.7 rule, the z-score all assume normality. Chart averages, and when you get that assumption for almost any underlying measurement, a strong license, and why X bar charts are so robust. But it says nothing about individual values. The chart of individual inherits the raw data's shape, skew, bounds, and bimodality. The theorem has conditions, the finite variance and independence. Fab data sometimes violates independence. Conjugating lots through the same chamber are correlated, and a run-to-run controller correlates deliberately. Real issue, lecture 3. But as a justification for charting averages, it is sound. In practice, the departure that causes trouble is autocorrelation, not non-normality. Data about as non-normal as you will ever encounter. The parent is exponential. N equals 1 is the raw data, strongly skewed, piled against 0, long tail right, nothing bell-shaped. N equals 2, already less extreme. N equals 5, the subgroup size you will actually use, visibly more symmetric, a slight right skew, the worst is gone. N equals 30, essentially symmetric, hard pressed to tell it from a normal by eye. N equals 5 is already dramatically better behaved than N equals 1, even for this extreme parent. That is the practical justification. You do not need N equals 30, you need residual skew small relative to your control limits, and for most fab data much closer to the normal than the exponential you begin with. So here is the consequence. X bars are robust, they plot averages, so the central limit theorem works for you. Moderate non-normality barely moves the false alarm rate. You can apply them without checking the distribution. IMR charts are not, they plot individual measurements, so the charts inherit the raw distribution. Skewed data gives us a asymmetry false rate, too many alarms on one side, too few on the other. Check normality transformation first. And individual charts is the one you will not use most in fab. Metrology is expensive and a huge number of real applications. You measure one side on another one, no subgroups. So the chart with the weakest assumption is the one that from fab lean on the hardest. The convenience chart is the fragile one. Last stretch. Let me reframe everything we have done. Has the process changed? That is the only question. Every control chart, every run rule, every anomaly detector in this course answers it. And notice what kind of question it is. A noisy signal, and we must decide automatically thousands of times a day across a fab whether what we see is consistent with nothing changed. That is statistical inference, and that is the hypothesis testing whether or not we use the word. It is the bridge to the rest of the course. Build a classifier on sensor data later this semester, and you were doing exactly this, a binary decision from noisy evidence to errors and the threshold you choose. The vocabulary changes, precision and recall instead of type 1 and type 2, ROC instead of ARL. The structure is identical to what Schubert faced in 1924. So let us spend the last 15 minutes making that structure explain. Type 2 error, the misshift. The process has really changed and shifted to by a full standard deviation, the gold curve. The chart says nothing. 84% of the lots from this shifted process still landed inside the limits. How large is that shift? It takes a CPK of 1.33 respectable and product worthy down to roughly 0.67, which is unacceptable, not subtle, and any single point still probably fall inside the limit. So how do we catch it? Two ways, both lecture 2. First, you wait. 60% per lot means the point outside eventually on the average after 6 lots. And that is the average run length, the standard measure of sensitivity. Second, much better, the shifted process puts almost everything on one side of the center line. 9 in a row is essentially impossible by chance, 1 in 256, but nearly guaranteed after a real shift, and this is what the run rule is for. Before this, let's name the other error. A false alarm stops a healthy tool, lost capacity and engineers weak, and worse, erosion of trust. The team sent chasing phantoms to learn to ignore the chart. Why 3 sigma? Let us interrogate it. A point beyond plus or minus 3 sigma happens 0.27% of the time by chance. One false alarm every 370 points. Chart daily, and that is 1 a month. Annoying, tolerable. You investigate, find nothing, and keep faith in the system. Now the alternative. Tighten it to 2 sigma and you alarm every 22 points, 1 a week, almost all false. The chart is ignored within a month and you are monitored in name only. Look at the curve. Extremely steep there. Small changes in K produce enormous changes in the false alarm. Schubert chose 3 as an economic compromise in 1924 for a pencil and paper chart. A convention, not a law of nature. No theorem says 3, so change it if your cost structure differs. Some fabs run 3.5 sigma on high volume products to cut the nuisance holes. Every threshold in this course is a business decision wearing a statistical cost. So now back to where we started. Same H-red data from the start of the lecture plus 1 line, the center line at the process average. What else do we need? A boundary. How far is too far? Set at 3 sigma with sigma estimated from the data itself from not an opinion. Giving a known false alarm rate of 0.27%, 1 in 370. Good. Then you have already built it. Let me just draw it. There it is. You have built a control chart. Every element came from today. The center line is the mean. The limits are plus minus 3 sigma with sigma from 5-step construction that we did on the previously. 3 sigma comes from the empirical rule and the average run length argument. The flag point is a hypothesis test at 0.27 false alarm rate. And it already tells you something. Lot 81 is outside the limits. One real line that fires an alarm and triggers an out of control action plan. So now there are 3 honest limitations All three are in lecture 2. 1. It says nothing about the specification. A point inside may be out of spec, one outside may be perfectly sellable. Control limits describe the process, spec limits the customer. The common error in this field. 2. It assumes independence, that the sawtooth says consecutive lots are correlated. 3. It has no memory, so a slow drift and a sudden step look identical. Run rules and EWMA fix exactly that. So in the next lecture, we'll talk about X bar R, IMR and P charts and the pattern inside the limits and capabilities. So let's look forward to the next lecture.